All right, ladies and gentlemen, we are going to get started with our task on rock identification. And this little bit of this week's material is meant to prepare you for your lab test, which is similar to the minerals lab test, where you're just going to get pictures. But if you look closely at those pictures, you can use our classic giveaways chart, which I've kind of shown to you in the notes sections, and then you can use your sedimentary igneous metamorphic charts to then kind of hone it down into whatever the name of the rock is. So I'm going to go through those processes with you many times over here, and we'll just kind of um, figure out how you would go about really uncovering what an unidentified sample is that is sitting in front of you in picture form. And it would be better, obviously, if we had rock samples that you could actually see, touch, and hold, but here's where we are. We're in a virtual world, and you're looking virtually at the first sample that I have for you, which is, I want you to just take a look at it. I mean, this is as dull and boring and as uninteresting of a sample as you might be able to find, and that's why I did this one first, because it tends to present students with a challenge when it comes to identifying it from scratch. Let's just think about how many different colors you see in this picture. And the answer is hardly anything. You see like a whitish tan and then maybe tan. It's kind of like basically the same color all the way across. You see a couple of little speckles or nuggets of crystal in there, and very isolated, one or two, and then there's a little actual spike of crystal right there. Very isolated though. The general rule here is we're seeing hardly anything in terms of crystals, hardly anything in terms of color variation, and absolutely nothing remarkable about this rock. So what that leads us to is looking at our classic giveaways chart. And this is how you start the identification process for any rock sample. So you have a choice right away whether you think it's sedimentary, igneous, or metamorphic. And that's why I gave you these kind of bullet point giveaways that might help you identify it. So let me get my red pen out here, and we're going to talk about what it isn't. And what this rock is not, I would say let's kind of look at all the words on the whole slide. I think glassy is a no. It does not look like a piece of broken glass or shiny or sharp edges or anything like that. It doesn't have gas pockets or bubbles. It doesn't have small or large interlocking crystals that are multicolor. Now, we will see what that looks like throughout this presentation. So this is definitely not it. There are hardly any crystals to even speak of generally, let alone interlocking and multicolor. Okay, so there's that. And then we look down at metamorphic. Here we're these two foliated and banding areas. We're looking for a pattern where you see very paper thin layers or some sort of arrangement of crystals within a sample. First of all, we hardly saw any crystals, so you really can't say that there's a pattern if there aren't any crystals in the first place. So let's just kind of eliminate those. Here's where I believe I would be confused as a student. I think, it kind of similar to a non-foliated where you have one or two blended colors, no real pattern, very bland and blasé looking. However, we should see lots of crystals visible. They may be randomly scattered, but they're there. And in that rock sample that we were just looking at, I don't see any of that. There's no evidence of sparkling or crystals or anything like that. So now that leaves me to look at sedimentary. And do I see bits and pieces of material cemented together? I don't really, I mean, you might consider those little speckles of black that are in there to be cemented in, but what you're going to realize is that those are just an isolated crystal, and that's not really what we're after. When we say bits and pieces, we mean like little pebbles or rocks, gravel, sand grains, things like that that are actually held together by a mineral cement. There's not really much evidence in that picture of any kind of grain that we're looking at. We're just kind of looking at a very honestly plain and bland looking uniform surface. So I wouldn't call it clastic, and I wouldn't say there's any fossils in it, which eliminates the bioclastic stuff. But Circling the crystalline description, uniform color and texture, we definitely have that. Isolated or no sparkles, we've got a couple of isolated ones, maybe. I think we've got a sedimentary rock here, and I think it's crystalline. Okay, so once you make that decision, and this one I'm telling you is for a reason, this is a little bit more tough. You can go then to your sedimentary rock chart, and that becomes really easy. Here's why. Because you have all the classic ones up in top, and I think I'm still on. Nope, I don't. Sorry, got to get on pen. Back to the pen. Let's pay attention. There we go. All right. Sorry. Back to the pen here. We eliminated all the classic ones because we don't have any bits and pieces that we think are cemented together. So all that goes away. Down below, you have bioclastic is coal. If you think it's a black sample that we were just looking at in terms of color, then that would be it. However, no, that was more of a yellowish kind of tan color. So our options are crystalline all the way, whether it's rock salt, gypsum, dolostone, or limestone. Here's the deal. If you think it's rock salt or rock gypsum, it should be clear or white. That's about it. There's hardly any variation in that. And actually rock salt may actually have kind of some swirls of impurities in it, things like that, because it's not necessarily pure halite, which we saw in the minerals lab, which is basically clear. But pretty much rock salt is clear to clearish white, maybe some gray. Rock gypsum, the same. It's going to be either clear or white. That's it. So these two really don't fit our sample that we have. Dolostone, similar to how we eliminated dolomite in the minerals lab, we're not going to see that here. So I'm just going to say no. Dolostone is a tough one, and it's not something I'm really honing in on you guys knowing in this particular segment of the course. So you don't have to worry about dolostone whatsoever at all. I think I maybe mentioned that in the notes already. So that really brings us down to one last option, which is limestone. And I want you to look at the kind of description. First of all, it's made up of calcite. Calcite is a whitish, clear to white to gray mineral that we saw. And that one was the one that fizzes in acid and has the rhombus shaped cleavage pattern, blah, blah, blah. That comes together pretty handily to make limestone when you dissolve the calcite in water and then let it slowly recrystallize. Now, when it recrystallizes, and this is what we're talking about within caves and things like that, it doesn't really form these ornate, gorgeous crystals. It just forms this dull kind of blah kind of looking, stalactite or stalagmite, or actually this can happen, near large bodies of water, things like that. So really what we're looking at there is limestone. So you may be saying, holy moly, how am I supposed to ever deal with that or remember that? Well, I have a solution to it. As I close off the ink here and I go back over, I'm not going to really make you try to identify pure crystalline limestone like you see here. I'm more after whether you know that limestone is very, very capable of actually collecting fossils. In other words, once living creatures, remnants, skeletons, shells of organisms, things like that. And if you look at this picture, this is absolutely incredible. This is very, very typical limestone. And if you compare it side by side with what we just saw seconds ago, color-wise, you're really dead on in terms of that kind of tan beige color, a little white here or there, but nothing crazy in terms of exciting color. So what this sample of number one would look like with fossils in it is what you see here. Honestly, I'm going to tell you right now, if you get this question on a lab test where you're looking at a picture and you're trying to find out whether it's limestone, I'm telling you right now, you're going to see very obvious fossils. This little area that I just highlighted looks like we had a critter that burrowed out a little hole within that limestone and actually once was living there and then for whatever reason died and got trapped in there. And the rest of the whole thing is just tons and tons of different seashells and other organism pieces that are cemented together. And that is the limestone that I expect you to be able to identify. It's kind of that yellowish tan color, but for us in the lab test, I guarantee you're going to see some sort of evidence of fossilization, creatures, once living creatures, being trapped within that. So that is limestone. I know it's weird, but hopefully I comfort you by giving you that there will be fossils for sure. Um, Plain old crystal limestone actually is a pain in the butt. It doesn't even necessarily have to be this color, depending on the impurities. It can be a lot of different things, but generally it's that bland, blah kind of not much going on, ugly rock. And that can be confused with a lot of other ones, so I'm not going to make you distinguish it. So look for fossils. Understand that fossils are sedimentary. Fossils mean limestone all day long. So the next one, moving quickly along here, it's a small picture. I'm going to show you this, that it's kind of blurry, but then we're going to zoom in on it in a second. What I hope you see are lots of different like granules, colors, and they're there. Now this could be confused with an igneous rock, which we'll talk about in a second. And I don't want you to do that, because what I hope you see as we zoom into the close-up view is these are all little bits and pieces, tiny, tiny fragments of broken up pulverized rock that are actually held together by mineral cement. So let me go ahead and zoom that one in to a better picture. And what you'll see, hopefully, is you've got little pieces, and within those pieces, if you look really carefully on this picture, you're going to see this putty color that kind of surrounds a lot of these crystals, and kind of it's sort of a very kind of whitish gray beige color that holds between these crystals, or not crystals, but these bits, holds them together. And that's the tough part about looking at a rock like this without a real good close-up view. You're not going to really necessarily know that, but you can see it within this picture, how they're being held together by sort of this, what we call a mineral cement. Now, if you were to feel this with your finger's going to run across all these little pieces, and it's going to feel like, well, honestly, sand. It's going to feel like sandpaper. And that's the critical thing that we have to look at. So you're looking there, and this is going to look similar to some rocks that we look at in the future of this presentation. But what I want you to understand is these are separated by this weird substance, which we call mineral cement. When we look at, say, an igneous rock that has interlocking crystals, you're going to see that they are fused together, and there is no boundary. And this, you should see that there's a little bit of stuff that may end up between or bonding these things together, and that actually can be undone. We can actually pulverize this back down pretty easily. But in an igneous rock, the crystals are going to be far more pronounced and look more crystalline, not just like bits and pieces like this. And there won't be any like gaps or putty colored stuff in between them. So just keep that in mind as we go into future samples within this presentation, where we're trying to look for interlocking crystals. For this one, though, this one is going to fall under the clastic realm of sedimentary rock, which would be bits and pieces of material cemented together. Now, the confusing part of that one is, am I looking at large or small interlocking crystals? You would be if there wasn't that weird, and some pictures are better than others, but you don't want that putty in between the crystals or chunks or bits and pieces if you're going to think it's an igneous rock. And when you see in the next couple of minutes here the igneous rocks that do have interlocking crystals, it's going to be pretty obvious that those are interlocking and not bits and pieces with mineral cement in between them. You don't see gas pockets or bubbles, and it's certainly not glassy, which we'll talk a little bit more about. Foliated means there's a pattern. Banding means there's a pattern in terms of crystals being aligned and seeing like paper thin layers and things like that, or a certain amount of shine. Literally, that rock definitely has none of that. For non-foliated, random visible crystals, you may see some sparkles within the one we just looked at, but there's not really, I would say it's not blended. The key point with non-foliated metamorphic is you're going to look at like a swirl or a blend of colors, not necessarily distinct colors. And certainly in that sample, we had definite grains or granules that were cemented together. So that would be why you would eliminate the non-foliated metamorphic rock. So we were leaning on classic. This one did not have fossils at all, although you can find buried bones and imprints within sands. I almost gave it away. Within this kind of sample, this particular one didn't have them, but we do have those bits and pieces. Crystalline, we talked about with limestone. You have a uniform color texture with isolated or no sparkles. This one is a little different than uniform. There's actually grains and grit to it. And so it eliminates that crystalline. And I know you're thinking, well, crystalline, doesn't that mean it's like super ornate and shiny or sparkly? You know, in sedimentary world, I wish that were true. It isn't. In a crystalline sedimentary rock, you get something like limestone, which is typically pretty boring. This one, however, had bits and pieces, grit, grains that were stuck together. So we're going to go with classic sedimentary, which if you go to this chart, that eliminates the entire bottom half of the chart. So you literally can eliminate that, cross it all off. We talked about how we're going to kind of eliminate breccia for this portion of the course. I love it. It's just not something you're going to see a lot of. So you're down to conglomerate, sandstone, siltstone, and shale. And why I said that is that we said it was clastic. So that's the top half of the chart here. Now, are those pieces that you saw within that rock that are cemented together pebble or cobble size or even boulder size? No. Boulders are gigantic, so that would not be what we're looking at in the zoomed in picture. Pebbles, they're more like driveway gravel type size. Cobbles are like cobblestone streets in older European and Northeastern cities. You can actually still find a few cobblestone streets out there. Terrible to try and shovel snow from. So I don't understand that, but it was a good thing to do. They're pretty big though. They're about as big as your hand or bigger. So what we saw in that picture were not pebble or cobble size. So that eliminates conglomerate and breccia if you were thinking about it. We're down to sand, silt, and clay. Now, if you threw that rock into a puddle of water, would it kind of poof out and create clay? I doubt that. Clay is the tiniest of tiny sample grain size samples. So you're not talking about clay in that picture. That would be something you couldn't even see, to be honest. Silt, also difficult to see, but that's kind of like dust that you kind of, if you were ever to shake out a rug or beat it against a post or a tree or something, and that very fine stuff that comes out of that rug, that is silt. We're not talking about that. That's a little too small. So we settle in on, as I gave it away earlier, sandstone or sand size, which means you have sandstone. Now, if you were to feel that and imagine that with your fingers, you'd be feeling sand texture, which means you're feeling almost like you're rubbing your fingers on sandpaper. And that, or an emery board, if you do that with your nails, that is sand essentially glued to a stick that you use to file down your nails. And that's kind of what that rock would feel like. And I'm going to go back to that picture now and refresh your memory because it's been a second. So hopefully that kind of makes some sense as to why, not that one, that was limestone, why that would be considered a sand grain size, and why if you were to touch this with your finger, it would feel like sandpaper. And it's all glued together with this weird putty color that you kind of see in the detail of this picture. So that is sandstone. And we will move on to our next mineral or rock. We're up to sample 3 now. And this one's pretty stinking obvious, I hope you'll see. So let's take a quick look at that. What are you seeing? Well, clearly the colors are alternating where you see kind of like a black, white sort of situation. There's also one classic thing. I want you to look at how it almost looks warped or kind of swirly. Let's go with that. So I want you to appreciate that swirliness is a guaranteed one thing, and if not the different bands of color, certainly that swirling, which is called folding within a certain kind of rock, which we're about to get to. So I want you to see that, and then we'll go over to the classic giveaways really fast, and we'll kind of blow through this pretty quickly. Clearly, there's a lot of things you don't see here. No bits and pieces of material, no fossils, not uniform color or texture. There are sparkles in this rock, but they're in a pattern, so that is not going to work. Interlocking crystals, multicolor, small or large. The only reason I can't say that is because they're clustered in a pattern. Again, this pattern thing where we're seeing alternating color bands, huge for this. So we can't say this, that they're interlocking, which again, we'll see interlocking shortly. Gas pockets, bubbles, no. Glassy, no. Foliated, if we go down here, it says we have minerals aligned in crystal layers. That's exactly what we're looking at. The layers are so thick that we can consider it banding. And actually, the word I was thinking of earlier is distortion. They're literally bands of almost like stripes on a zebra that are actually kind of swirled, and that's extreme foliation. So we are arriving here at a metamorphic rock. So if we shift forward to the metamorphic rock chart, all the non-foliated ones and the ones I told you don't have to worry about are at the bottom. So that we're literally down to 4 choices already. So hopefully you're feeling good about that. And then if you look at the texture, we're all foliated. That's why we're up here. Mineral alignment for sure, but we're actually in the banding category where it's so completely obviously separated into different color bands that makes this rock nice. It's a nice rock. It's a classic metamorphic rock. And you can even see in the picture where they show the bands and they're kind of swirly. It's a hard one to miss, to be honest. So that's what we're looking at there. I'm going to get out of here, discard those again. And so yeah, that's where we're at. All right, so we will move to the next sample now. I'm going to slide this over. There's our nice rock sample again. So we'll get rid of that. And we'll go to sample 4. This one's one of my favorite ones to look at, but they're all my favorite because I'm a nerd. What I want you to see here, this is actually a little confusing when you compare it to sandstone, which we saw earlier. And honestly, doing this virtually, it's a little tough to see what I'm about to talk to you about, which is the interlocking crystals situation. It is fairly uniform in color, but I want you to see the scattering of little black speckles in this, and it's again not showing as kind of flashy reflection in those speckles, but they're there. There's also a couple of bits of white material in there, grayish white material, certainly along those edges, and there's a couple of areas of white crystallization there. And here's the tough part about this. If you were to actually see this, all this pink, you would see little baby, like absolutely minuscule little tiny crystals of that pink stuff, which is actually potassium feldspar, a mineral we were looking at earlier. So it's again, with virtually in pictures, we're not going to be perfect at this, but there are a lot of different crystals scattered about this. And in the light, if I could show this to you under a flashlight, you would actually see little sparkles, really pretty randomly, but fairly evenly scattered about this rock. So they're little, they're crystals, and they're interlocking. So if again, we're getting faster at this, I hope, as we go, but that would mean you can eliminate it. The only one I would be confused with is a classic sedimentary rock, but if you were actually able to see this under an actual light, you would see that this is definitely not that situation, where we had the little bits of grains cemented together where you could see almost a putty that was holding them. These crystals there's nothing putty holding these crystals. They're all connected to each other directly. And they're actually considered a small interlocking crystal in this. And so I also wanted you to take a look back here at the sample one more time. And tell me again if you think that sample is a light color or a dark color. And you can kind of probably guess. Overall, except for those black crystals that are kind of embedded in there, this is a fairly light color rock. So that's an important observation to make. when we're dealing with interlocking crystals, which we just said, according to this, was an igneous rock. So if we go to the igneous rock chart, watch what happens when we try to identify it. You get the color scale right there, and you go there, well, the dark ones are all over here, so that's none of those. The ones that are kind of, you would think of as a middle shade of gray are right here. So we're eliminating all these other ones on the, basically on the whole right 2/3 of the chart. We have pegmatite, granite, rhyolite, vesicular rhyolite, pumice, and obsidian. That's what we're down to. Now, if you look over, obsidian says usually appears black. Well, the one we were just looking at certainly did not, nor did it have a glassy texture, so that's out. Pumice is in the right color area, but it is also glassy, and believe it or not, as you probably saw earlier, pumice is actually a vesicular rock. If you follow from the name of pumice all the way over to the right, you're going to see gas pockets. So that's not going to work for this particular sample, nor is vesicular rhyolite, because vesicular tells you it has gas pockets. So we're going to cross that one off too, because it's vesicular. So down to 3 options. Now, how big are the crystals? Again, texture for in a rock world is how big are the grains of the crystals? Are they really small? Are they fairly large, or are they gigantic? Well, we just said it was kind of a small crystal size. They're almost to the point where you can't see them in that horrible picture. So what we're actually looking at is plain old rhyolite. And rhyolite is awesome because actually if you draw an arrow down, you can almost see what or why that color might be there, because it's got a lot of potassium feldspar in it, and it's pink. And that's what this whole thing at the bottom of the chart is talking about, because it gives you hints or clues as to what colors you might see if you're looking at a rock. So for granite, I could also see speckles of pink or white or black mixed in. But for rhyolite, you're going to see mostly pink with a few isolated black crystals and some isolated white ones. So it's kind of a neat, I know I just basically made a mess on this chart, but hopefully you're kind of agreeing that, hey, we're looking at something that's really light in color, small crystals, not vesicular. That makes it, by process of elimination, rhyolite. So rhyolite, you can think of it as the pink rock that has some sparkles and that has some very clear sparkles of black crystals, some white crystals, and some mostly pink ones. So, all right, that brings us to sample 5. Got to move right along here. This one, I'm hoping you can see that, again, it's kind of looking like almost like sugar, a lump of sugar, but you can sort of see it's all kind of a one or uniform color, maybe a blend of like white and sort of a whitish gray. Again, without a flashlight, you can't see. There's a lot of sparkling going on here. You can almost kind of sense that. Maybe if I had a flashlight and I could point it at a picture and make it light up for you, I would. But again, on a lab test, I would tell you, hey, this shows sparkles under a flashlight. I mean, I'm going to give you that hint. So we're looking at a fairly uniform color and texture that does have crystals. They're not multicolor. It's mostly 1 or 2 very, very similar colors. And I don't see any evidence that there's like mineral cement or grains of things in here, like pieces of stuff that are cemented together. So if you kind of go with that, back to our, again, classic giveaways chart, moving along. We have interlocking crystals, but they are not multicolor. So we are going to eliminate, let's go through that process where we kind of eliminate the interlocking multicolor issues. No gas pockets, not glassy, not bits and pieces of material cemented together, no fossils. Now, here's where you get confused, because you see the word crystalline and you think, oh, there's got to be sparkly, beautiful crystals in it. No, it just means that you've got a uniform color and texture, which even still makes some sense. But when you look at my parentheses, you're not going to see hardly any of those sparkles. Whereas this rock, if you were actually looking at it in the light, has all kinds of sparkles. So we go down to metamorphic. I don't see any minerals aligned in crystal layers or bands or anything like that. But if you read our non-foliated definition, we've got random visible crystals, 1 or 2 blended colors, not really in a pattern, they're just kind of random. And that's what we're looking at. So here it is. we have a non-foliated metamorphic rock. So we're going to forward up to that chart, cross off the whole top half because those are all foliated. We're in the non-foliated area. And you have to decide, well, how big are those crystals and what am I really looking at? I told you already, by the way, that the hornfells was a no-go and the conglomerate's a no-go, so you're not going to see those. Is it a black rock? Well, I think it's quite the opposite. In that case, it's a highly white-looking rock. For this one, there can be black swirls in it, and if you've ever seen tiles of this substance, you would know that. And so it's not impossible to see black, but what you'll see is it's predominantly not black, but the swirls that you might see in it actually might be in a black family. But for this case, we are not looking at coal. That was certainly not a black lump of coal at all. So you're down to quartzite and marble. And here's the deal. How big are the crystals? Are they fine or on the more coarse side? Also, if you look at what sandstone might look like before it becomes metamorphic and versus limestone, we already saw both of those. We saw sandstone being maybe a reddish to brown color. At the most, it's going to be like a gray color. And we could metamorphose that, and you should see that color reflected in the rock if it were quartzite, which we will see in this lab. But limestone was on the very, very light side of the color family, as is the mineral that's predominantly making up that sample, which is calcite. Calcite is clear or white almost all the time. So if you look at the evidence here that we're seeing, we are looking at marble. Now that, again, marble takes on a lot of different appearances, but if you're looking at just straight up basic marble with the lesser impurities and other weird things that can go on in the formation of marble, that is what we're talking about. So it'll appear either kind of a slightly pink color or a white color, and there's how you get marble. So that's what we were looking at with that one. So I'll escape out one more time. Move right on to the next sample. And I do have two pictures of this one because you can see the same thing that I'm going to call out here in both pictures, but this one is just a quick starter pick. There we go. It's enlarged. All right. So here's what you're looking at. First, I guess the best thing to look at is, do you see on the lower part of this rock where you have like little, almost looks like there's flakes in there, or like you could almost put your fingernail in there and kind of split this apart. You can't, but it looks like you could. And those are paper thin layers. You're also big time seeing a shine. Now, this is really evident in this picture where you see a lot of this top surface of this mineral shining due to the light that's reflecting off of it. And that has to do with the fact that there's crystals in there and they're all kind of flattened out so that when the light hits them, they all reflect at the same time. So you see a lot of glare across this whole rock. And I'm actually going to point out these little brownish red nuggets in here that you see. Those are actually garnet crystals, which happens in an amazing case of metamorphism. So, oops, I gave it away. So you have a shine because of the aligned crystals, wink, wink. You also have these little paper thin layers that you can see on a side view. And I'm actually going to pull up the other one of this same rock. It's a little different sample, but you'll see sort of the same action going on. And this is a big, big piece, but you're hopefully can hone in on some of the kind of paper thin layering going on. Those are all mineral crystal layers, and you can still see evidence of the shine on this. This is just such a big sample. It's not as obvious, but I just wanted you to look at the micro thin crystal layers as you see, and then that surface shine that you get. And when you go to our dead giveaways chart, I say dead giveaways, it says classic, I don't know, whatever you want. I don't see bits and pieces of material cemented together because there are lots of crystals, not chunks of stuff. No fossils, and I'm sparing you the ink this time. No fossils, not a uniform color or texture without sparkles for sure. So that eliminates all of sedimentary. Large interlocking crystals, it does have some, and they are multicolor. So I would be tempted to pick that one. However, if you look down below, the crystals are aligned in layers. There's a pattern or an obvious sheeting, like a little evidence. It's almost like several pieces of paper stacked on each other. And that's what we're talking about here. So that is minerals aligned in crystal layers. There are those weird garnet crystals in there, I'm not gonna lie, but they are locked in pretty tightly. But the pattern, if you ever see a pattern, that overrides everything. If there's a pattern in your crystals that you see, automatic metamorphism automatically eliminates all of igneous. Obviously, there's no gas pockets in a classic. So this is a foliated metamorphic rock. I'm not saying that they're in bands necessarily, so it's not like super extreme where you see alternating light, dark, light, dark, light, dark, but we do know this is metamorphic. So you can eliminate all the non-foliated metamorphics right now. You're down to 4 options. You talk about whether we saw banding or not. That's that little guy right there, which means nice. That is not what we're looking at quite yet. And then you look at the overall grain size. Those garnet chunks in there are a giveaway that we are not on the fine side of things. Those are big. So if they're actually bigger than medium, to be honest, but the other crystals that are reflecting that silvery color are actually mica crystals. They are platy mica crystals that are very obvious, and they are very aligned so that you get that glare. So what we're looking at is a giant piece of schist. And I said that way. Hopefully you had a chuckle because it was a big piece of schist. And actually, with the garnet crystals in there, which if you look at the composition, you can actually have plenty of garnet within a chunk of schist, but we have chunky schist because of all those chunks of garnet in there. So you can make a joke about that at the dinner table tonight. That is schist. All right. So I'm going to get back out of here. We'll move right to the next one. Move right along. I forgot where we were. There it is, number 7. We're getting there. All right, now this is another one that I hate because it tends to be mysterious when it comes to trying to identify it. So I want you to take a quick look at it. And tell me, or tell yourself, how many real colors do you see in this thing? I see like some brownish pink with some lighter pink and an occasional nugget of something else, but that could just be, who knows, based on the picture. So we are looking at about 2 tops that are very consistent blended colors in this. So, and they're blended because at any moment it's just switches from one to the other. The other thing is that you can almost tell that, again, under some good light, this thing would sparkle, where we'd see some sparkles from in this area. This would be one big sparkle. This would be some sparkle. Again, without being able to shine a light on it, I can't really help you with that, but it's a little bit sparkly. It's 1 or 2 blended colors. And what I'm not seeing are, for example, interlocking really distinct multicolor crystals. I'm not seeing bits and pieces or grains of things that are kind of cemented together. It's just sort of a blend. And that tends to make my mind think that this was really heavily heated and kind of swirled around almost to the point of melting. Okay, so let's think about that. Go back to the chart. And I know we've been through this several times already, that you're already thinking what I'm thinking, I'm sure. We eliminated a lot of the other things, like such as bits and pieces of stuff cemented together, no fossils. It is kind of a uniform color texture, but there are going to be a lot of sparkles in it, and it's not going to fall under the sedimentary version. Certainly not glassy or no gas pockets. Interlocking crystals, yes, but there's just not enough different coloration there to make me think it's multicolor. So I'd cross all that off, which means not sedimentary, not igneous. Down here, I don't see a pattern in those crystals at all, so it's not foliated. Certainly not banding where you see alternating light dark. But do we have random visible crystals? Absolutely. 1 or 2 blended colors without a real pattern. Bam. Non-foliated, metamorphic. You go back down to our chart once again. Non-foliated means you eliminate the top half. So again, if you missed that, that's non-foliated. We can eliminate, or let's just kind of go through one at a time. Coal, is it black? No. Hornfels? No, because we said you won't see that. Quartzite is a possibility. Marble is a possibility. Metaconglomerate, that's, you're going to see pebbles that are stretched and distorted, and I also told you won't see this anyway, but no. So you have a choice between quartzite and marble, and then I go back, we actually just did marble recently, so I talked to you about how quartzite comes from sandstone, which is a reddish brown to gray color. And then limestone is more of a yellow, white to very, very light gray color. So if you kind of think about that, that's going to help you. Also, the grain size. In marble, the sparkles are much more obvious because you have a slightly more coarse texture for marble. Quartzite tends to be more of a fine texture, and that's what we're looking at. So quartzite is that blend of very similar colors, lots of sparkles, but they're random. And sandstone. You can get different sandstones, which can result in different quartzites, but for the most part, you're going to see quartzite looking like it's going to be that orangish, brownish, reddish, pink color, all blended together. Or you could see it as more of a purple version, or you could actually see it in a very rare circumstances with just a bizarre set of events where you could get a greenish looking one, believe it or not. But for us, that's a classic sample of quartzite. So end that story right there. So we will go back over to our next sample. So that'll be number 8. And that's one of my favorites. Oh yes. You might actually see this in some of your countertops around this area. Okay, so here's what you're looking at. Take a look and count how many colors you see. I see a lot of black and white, black and white, black and white. I also see a little bit of pinkish stuff in there. But we are looking at definitely different colors. Now, do you see any evidence of kind of a putty colored stuff that might be holding this together? And the answer is no. If you look at any two crystals like this black one that I'm going to kind of point to and hover over there, that is directly connected to all the white ones that are around it. Same with this pinkish one and the white ones around it. I mean, this is what you are seeing in what I would call interlocking crystals. If I were to go and try and grab any one of these black or white or pink specks out of here and just kind of grab it with my fingernails, I'll probably break my fingernails because they're not going anywhere. They're fused together, they're interlocking. So that means, and now I will really start to speed things up, if you see interlocking crystals, that puts you in the igneous world. And these ones, so we'll get to whether you call them small or large based on just a picture. It doesn't matter right now. Small or large interlocking crystals, either way, that makes it igneous. So one thing I will talk about, though, is if you look back at the sample, which I want to one more time, do you feel like it has a more of one color than another? I guess is kind of a weird way of saying it. We have and hopefully you're agreeing with me that this is like a 50-50 blend. Like for every one of these little black specks, I'm going to see a lot. Like if you added up all the black crystals and added up all the white crystals, you're probably going to see about the same amount. So that's a very important thing because that makes this rock in a black and white world come out to be sort of in the middle. Like it's going to look kind of middle of the road gray, maybe with some speckles of darker color in it. So I want you to, now that we know it's igneous, to see where that might fall, because we talked about how color is one of the first things we're going to do. Is it light or dark? Well, it's got a lot of light ones and a lot of dark ones. Guess what that averages out at? Right down the middle. So let me show you, and I made a pretty horrible, let's get rid of that thing. So we're right down the middle, and that, if you kind of look at the lower part, you're going to have white and gray ones and some black ones. So if you look at the composition area down here, that's kind of where it does fit. So that being said, I wouldn't call it an overall light rock. So that eliminates basically it could eliminate pumice, and it definitely does for another reason. It doesn't appear black right now, so it eliminates obsidian. All of these guys over here, those are dark, like as in almost they're on the very dark shades of gray kind of thing, and certainly we're not looking at anything green, so it's not those. So you have the options of pumice, possibly, very light, unlikely, but possibly pumice, vesicular andesite, regular andesite, or diorite. Okay, let's deal with pumice and vesicular andesite. Is this rock that we just looked at, does that have gas pockets in it? And the answer is no, and not at all. So that does in fact eliminate pumice. It does in fact eliminate vesicular andesite. So now you're down to just two choices. Well, how big are the crystals? Are they fine? Are they really, really so small that it's almost hard to even tell that they're there? I disagree with that. I have a feeling that we're looking at a coarse, textured igneous rock that is really balanced between light color and dark color crystals, which means, yes, we are looking at diorite. And diorite is actually a common countertop material. When they find a good one, you will see homes throughout Texas, especially, that have you'll almost blindly call it granite countertops, but it's actually diorite. So that can happen. All right, so let's discard that, move back out. That was diorite. One of my favorite ones. You can definitely see lots of cool crystals in it. And we move to sample 9. We're almost there. This probably is my favorite one ever. If you've ever gone around, since you're in the Dallas college system here, let's call it that, you may have gone to, especially within Dallas and actually in Las Colinas as well, places that have a lot of this stuff lying around. And I don't mean lying around. I mean, it's part of the buildings, it's part of the sidewalks, it's part of the curbs, the street curbs. So I want you to take a look at that. And I want you to talk to me about whether you think this is a lot of colors or just one or two blended colors, or whether you think it maybe are bits and pieces of things that are stuck together by a putty of mineral cement. And I'm hoping that you're kind of like, wow, these are, look at these are giant. There's a big crystal of what I think is potassium feldspar. Here's some crystals of garnet. Up here, some biotite or some amphibole. These big pink ones are potassium feldspar. The white ones might be plagioclase feldspar. You might, if I look closely, some of the whiter ones, the lighter colored ones might be quartz. So you have a huge variety of minerals that are within this, and each one has its own distinct color. And they're all stuck together. So if I wanted to take, let's say, I'm going to pick this little, it's a grayish white color crystal right there. If I want to pull that out, that's not happening. It is fused permanently to the crystals around it, and we call that interlocking. And I hope you agree with me that these are very large in terms of size, just looking at what's on your screen. One other thing that you can see on this sample, which I think is kind of neat, down at the bottom, do you see how it's got like a flat side to it? Actually, all the sides are flat. That's because this has been cut and maybe even polished. And that's because that happens a lot with this kind of rock. So let's go over to the giveaways chart and knock this out. So I'm looking at a sample that has large multicolor interlocking crystals. So clearly we're in the igneous rock area. There's no pattern to the crystals. There's no putty cement holding bits and pieces of stuff together. I don't see any fossils. I don't see any pattern in those crystals either. They are really, really random, if anything. So that brings us to use this chart once again. And you have the option of, oh, maybe we should go back and look at it. Color-wise, what did you think about that? Do you think it was a dark color rock in a black and white gray scale world? Well, let's take another quick look. So black and white world, gray scale, how do you feel that this rock rates? And I'm hoping that if you were to look at this, put on the special glasses that made you see grayscale that like maybe some animals do, they would see this as a fairly light object. Okay, so this is very light in color, despite the isolated, there's some black ones in there that are in garnet is actually pretty dark, which is what that is. So it is kind of light. So what I would do in terms of this chart is shade, let's cross off all the darker ones. I don't really think there's enough of the black crystals within that to think that it's a middle of the road one, so that eliminates all those. So we're really just down to obsidian, pumice, vesicular rhyolite, granite, pegmatite. And we already talked about obsidian several times, how it usually appears black, and it's glassy in texture, very uniform, so that's not that. We're going to look at obsidian in a few. Pumice and vesicular rhyolite have gas pockets, so it is not either of those. That rock had no evidence of gas pockets. Rhyolite we saw earlier. Rhyolite is pink, and the crystals are really, really small because rhyolite has fine texture. That the size of the crystals is just small. So you're down to coarse or very coarse granite or pegmatite. Now, you got to see pegmatite to believe, but if you look at the size, I wish I had a button that could clear all the ink. I wonder if it can. No, I'm just going to erase. I'm going to erase a whole bunch of stuff. And we're going to look back at this chart because there's some evidence over here. Are those crystals 10 millimeters or larger, if you were to guess? Now, 10 millimeters is a centimeter. So literally, think about a dice that you would roll in Las Vegas, like a dice, is it a die, a single die? I don't know. They're a little bit bigger than a centimeter. Those are big crystals if you're thinking about it in terms of crystals. This sample is a smidge smaller than that. They're not that big. They're pretty big. They're 1 to 10 millimeters for sure. And that makes this guy granite. And you probably already do that. You've probably seen countertops, and you probably might even be thinking about some of the buildings that I was talking about within Dallas and Las Colinas that literally are made of this stuff. The ones with a lot of pink in them, like this one, are a little unpopular when it comes to countertops these days because people want more grayscale coloring. But you can go to houses that actually have this stuff as their countertop, and that's granite. Now, if you look at the texture, it is really rough. Lots of different jagged crystals that are interlocked together. What they do is they actually cut the stuff, kind of like you see in the picture on the bottom there, and then they polish it to make it nice and shiny, and that's how you get granite countertops. Now, if you're looking around in Las Colinas, if there's still any left, you'll see some of this that makes up the curbs on the streets because they were rich at one point enough to have their whole city basically made of granite. The William Square building that has the copper Mustangs out front with the fountains and stuff, if you look, the whole building is made of this stuff. Just go walk up to it and look at the outside walls and the sidewalks around it, and you'll see it. So granite is amazing. It's such a great durable, hard rock that is difficult to penetrate with water and stain and stuff like that. So it's really a great substance and very useful for tiles and counters and things like that. And that brings us to our final sample here, number 10, which is hopefully, I want you to look at this and hopefully agree that it looks like this thing's pretty easy to break. It looks like it's been broken pretty easily and things have fallen off of it. There is an evidence of layering. Now, different from what we're talking about in a metamorphic world where they're really, really thin layers, these are thick layers. And it almost looks, I hope you think that it looks like mud that's been kind of dried out, or clay, wink, wink, that's been dried out. And that's exactly what we are looking at here is basically dried out clay. So if there's one way to recognize this particular rock sample is, does it look like dried out clay? It's gray. It is flimsy looking. There's a lot of sharp edges because a lot of this stuff, just by handling it, will break apart. If you hit it with a hammer, it would pulverize pretty easily. And that's because these are very, very, very small sediments, tiny, tiny little pieces of clay that are all being held together by mineral cement. And they're so small you can't see the mineral cement. Maybe you can a little bit. But it's just the finest particle that we can get, which is clay, that's still actually visible to our eyes. And if you were to hold this, you would maybe get some kind of grit or greasy dust in your finger prints. Actually, it's so fine it gets into your fingerprints, and that's evidence that you're handling a clay-sized sediment. And it's so flimsy, and it is being held together, but very loosely, that you can actually pull pieces of this clay-sized sediment out, and it can actually get on your fingers, or if you use your fingernail and scrape this, you'll get this super, super duper fine dust, and that's your clay-sized sediment. So back to the dead giveaways, I mean, that makes this a classic sedimentary rock, believe it or not. And it eliminates, just looking at the picture, it eliminates large interlock. Sorry, got to get the ink engage your pen. There we go. It eliminates the interlocking crystals, no gas pockets, not glassy, not foliated with crystal layers at all, no banding or distortion. It's pretty uniform in color, but there are no crystals whatsoever evident. There are no fossils, and I mean it is uniform color texture, but um, you can actually extract those little bits, those clay-sized bits. So, if you were handling this, you would definitely be able to tell that it was a classic rock, not a crystalline rock, because you would be like, what is all this dust in my fingerprint within actually the pads of my fingers? And that's pieces of that stuff that actually rubs off of that rock sample. So this is going to be a clastic sedimentary rock, the smallest grain size you can get. So all the bottom part of the sedimentary chart's gone. Classic it is. Not pebbles or cobbles, not sand. Even silt's a little too big. Silt is dusty, where you could actually get it to be kind of in the air a little bit, and certainly you would see it around the rock, or just by rubbing it, you'd see a lot of dust. But this is the greasiness to it, that it's because they're so small, they actually interact with the oils in your fingers, make this sediment size clay, which means you are looking at shale. Now, if you look at the comments that I just drew an arrow through, compact may split easily. So hopefully you're thinking, wow, it's like mud that's been kind of compacted and it's stuck together now, but it doesn't take much to split it up. So that is a classic example of shale. So that is that. Okay, that brings us to the final portion of this presentation, which is our what I call the black rocks, or the rocks that are dark and super dark in color. And so we're just going to kind of go through side by side what they look like right next to each other. And we're going to just show you all of them in one quick rip. So there's 1 and 2. And I'm going to open up the third one and make that a little smaller. And then I'll open up the fourth one, which is that guy. And so we'll kind of click our way through. What I want you to identify first, probably, is the level of shine that we have, and also the level of kind of the sense that you might get of hardness on these things. Like this one on all the way to the right, kind of looks pretty tough. This one that I'm moving around right now looks pretty tough. This one looks tough, but if you look at it, it looks like it broke a lot. So maybe not so tough. And then this guy right here, if he's maybe we can zoom in a little bit on that. It looks almost like we have little mini layers, and it kind of looks a little bit flimsy almost. So what you're seeing, and also I want you to rate, or in your brain kind of think about overall who's shiniest. This one's super shiny. The one on the left is super dull. The one in the middle here is probably the shiniest of all, even though you're not quite being able to see everything. The one on the right is definitely dull. Okay, so what are we talking about here? All right, we have 4 different rocks. Here's how you figure out where we're at. Let's do the most probably boring one first, and it's the one that looks the least shiny. So that left to right, that one, and number 4 here, those are fairly shiny, or at least more shiny than this one. So what are we looking at here? Okay, this one has no similarities with all the other ones. You see all these different black and white crystals, and they're interlocked together. They're small crystals, and again, with light, you would see them sparkle. That is not happening with any of the 3 other ones. So we have and also the shine factor is just so absent on this, but you would see little sparkles, just not a shine. So what does that mean? We're talking about, let me go back here. We're talking about small interlocking crystals on this, which makes it an igneous rock. And also the color overall on a shades of gray scale, that is kind of on the dark side. So if you go to your igneous rock chart, let me make this bigger. The darker igneous rocks are the ones on this side. Oops, gotta get the pen going. This side Okay, and it's not green, so we'll eliminate those. We also said the texture was fine, so that makes it possibly vesicular basalt, or diabase. And I didn't mention this, but you don't have to worry about diabase in this lab, although you can definitely tell this is not diabase because of the crystals being what they are. Really, you're down to vesicular basalt or basalt. Do you see gas pockets in it? No. So you are looking at basalt there. So basalt is a fairly black rock with very, very small white crystals all interlocked together, very evenly spread out or spaced out. And on a flashlight, you'd be able to see random sparkles pretty much around all over on this, but they're really small. So that's just basalt. If there were little gas pockets in it, it would look identical to this, except gas pockets in it. That would be vesicular basalt. So this rock with the little holes that you would see for bubbles that had tried to escape when it was forming, that would be vesicular basalt. Same color, same everything, just highly vesicular. All right. Now we are going to look at these three. I'm going to ask you which one looks like a broken up piece of glass. That one, or that one. Definitely this one does not look like glass. This one, maybe, but glass, if you were to like take a beer bottle or a wine bottle and break it, I don't know why I just went with beer and wine there. This must be what's on my mind. But you're not going to get a pattern that looks like that in pieces of broken glass. This absolutely, to me, looks like broken glass. And here's the difference. Look at the curved break lines, the fracture lines. They call it conchoidal fracture due to these curved snap lines when it was either chiseled or hammered out of wherever it was originally, because this was pure lava actually when it was formed. So you got to literally break it out. So, and it looks like a big piece of glass. So that is the epitome of glassy texture within our rock world. And glassy texture means one thing: igneous all day. And when you look at your igneous rock chart, you only have some select options there for glassy. So let me get those out. And here they are. You have obsidian, pumice, basaltic glass, scoria. Now, the ones that have vesicular texture in addition to glassy texture would have gas pockets. That one had no evidence of gas pockets, just glassy texture, plain old glassy texture, which means you're obsidian or basaltic glass. Now, basaltic glass is going to have, it's just not the same. It's glassy in the sense of how it feels and how it sounds when you clank it against stuff. It isn't quite the same as obsidian, which usually appears black. Bam, well, there you go. Obsidian usually appears black because that's 99% of the time the way you see it. And that's what we're looking at. That's a piece of obsidian, and a lot of you knew that going into this. Now, basaltic glass, I'm not going to make you distinguish between basaltic glass and obsidian in this lab, but you will see a slightly different color scheme within basaltic glass. It'll be mostly black, but you're going to have other greenish minerals mixed in there, and some more of that white to gray feel to it, and it just isn't quite the same. But I'm not going to make you figure out the difference between the two. If you see it that it looks like glass, like that one did, and it has those sharp edges and that kind of breakage, those conchoidal fracture lines, that's guaranteed to be obsidian for us. Now you mentioned, or I mentioned, that it says in that chart usually appears black. Well, what the heck? Why do they have to use a word like usually? Well, I've got a sample of that, and I'm going to move these guys over. I got one more picture of obsidian that was, I don't know where the whole thing went, but hopefully it's still there. Nope, I closed it. All right, so I'm going to show you one last picture of obsidian. This one I actually have in my collection personally, and it kind of found its way into my world. I don't know how, but it looks exactly like the one that was black that we saw just a second ago, which is this guy, except it's red. But if you look at all the sharp, jagged edges on it and the conchoidal fracture lines as it got split off from wherever it was, this is the same thing, except this one on the left, this is the one I have. It has a lot more iron in it, which is why it kind of got that reddish color as it was cooling off. So when it says usually appears black, that's like 98% of the time, but occasionally you can see a cool different color of it. Just depends on what metals and what minerals were around in terms of impurities when it formed. But I just wanted you to see, usually appears black doesn't mean always appears black, just most of the time. Yeah, you're welcome for that. Geology is cool. Okay, so that brings us to the last two. The reason why I saved these for last, even though they're marked B1 and B2, is because you have two possibilities when it comes to coal in rocks and mineral in our investigation here. And I wanted you to eliminate a glassy texture first, obviously with obsidian, and I wanted you to eliminate, like, just because it's a black rock doesn't mean it has anything to do with these two particular coal samples in terms of you'll see crystals, small, fine interlocking crystals in basalt, where this, you're not seeing any crystals. You're just seeing kind of a dull shine and then a really, really high shine. So these are the two samples of coal that we have. And if you go back, they don't really fit my rock classic giveaways, to be honest. Coal is a unique thing because it was formed from organic stuff, not necessarily by the standard processes that form rocks in terms of sedimentary and metamorphic. I mean, the one coal that we're looking at has a very high sedimentary origin in terms of compaction, cementation of stuff, but the stuff that was compacted and cemented was, let me get the pen out, dead plants and animals, sludge, tar, essentially, carbon. So the one sedimentary rock that is black, it's very light density, and even though it's compacted, it's still very light in density. It's black, but it does not shine. So there's some notes to take away. If you think you're looking at a piece of coal, look for a very uniform black color that doesn't shine. It doesn't look glassy, and it doesn't look like it has crystals. And that would be bituminous coal. So that's your sedimentary one. That's the B1 sample. So let me go back and just make sure you see that. That's the first one of the two coals, which is this guy right here. Okay, so it has a very slight shine to it, maybe very low density looking, doesn't look too sturdy, and it is doesn't have crystals. So that is the sedimentary version of coal, which is bituminous coal. Then you get to the shiny coal, which has all kinds of weird jagged edges, not glassy in terms of, you don't see glass looking like that typically. So if you go to the metamorphic chart, that's where it is. It's anthracite coal. The reason the shine comes out is because you added heat and pressure, which are the classic processes to form metamorphic rock, and that's what does that to the old bituminous coal. Let me just circle that, because if you take bituminous coal, the sedimentary one we just looked at, which is kind of less shiny and all that, and less dense, you add heat and pressure, you're going to make it more dense, and the crystals are going to start to recrystallize and shine a little bit harder, and that's why you get all that shiny, kind of weird jagged shininess to it. That is anthracite coal. So I wanted to kind of lump those rocks together like a lump of coal at the end of this presentation, because when you put them all side by side, they're very different. But when you're all trying to figure out, oh my gosh, I have a black rock and I know there's like 4 of them, I wanted you to see distinctly those differences between, say, a shiny anthracite coal, a dull sedimentary coal, a glassy sample of obsidian, and a very flat, dull-looking sample of basalt, but within that you see those little tiny baby crystals. So that wraps this whole presentation up. So hopefully that kind of helps you sort of see what you would expect. You're going to get pictures just like you did on the minerals test, on the rocks lab test, and you're going to use the dead giveaways chart just like I did all night long here, well, day for you or morning for you or afternoon, who knows. Um, and you then decide which chart do you go to. Do you go to sedimentary igneous or metamorphic? And then you fine tune it based on the appearance, the crystal size, the grain size, that kind of thing, and you should be good to go. So hopefully that was somewhat helpful for you, and we will see you soon.